This video will cover evaluating your models in R. By the end of this video, you should know how you can compare the predictions of models in R and what Model R functions are available for evaluating predictions. The code used in this video is available on the Learning Management System. It uses the data file dcelectricity_train.rds. You should download those now if you'd like to follow along. As we saw in past videos, you can evaluate your models using the loss function. The process you would go through is you would train a model, use it to make some predictions, and then compute the value of the loss function from those predictions and the actual values of the labels. The Model R library provides a useful function for computing prediction errors. It's the add_residuals verb. Like add predictions that we've seen in previous videos, it takes two arguments. The first is a model, and the second is the variable name where you'd like to save the residuals from the model. Residuals are the prediction errors, or the actual value of the label minus the predicted value. The table on which you calculate the residuals need not be the one that you use to train the model. It just needs to include all of the features and the label used in your model. Let's use that add predictions verb to compute the value of the loss function for some model. I'm going to load some setup code. Importantly, I'm going to load the data file dcelectricity_train.rds and save it in the elect tibble. The add residuals verb is part of the Model R library, so I need to make sure I load that library as well. Looking at that tibble in the Environment Explorer, you can see that it has four variables: the date, the high temperature, the low temperature, and electricity demand. This is very similar to other electricity data that we've seen in previous videos. Going back to my code, I'm going to train a linear model. The label is going to be demand. The single feature that I'm going to use is high temperature. I'll save that in Model 1. Then I'll use that model to add the residuals back to the elect tibble. And looking at the output, you can see that the elect tibble now contains an additional column, model.1.errors, which is the prediction error from Model 1 for each observation. Now that I have that prediction error, I can use it to calculate the value of a loss function. Suppose I'd like to compute mean square error. How might I do that? Let's take a look at my code. What I have here is an example of computing mean square error using those prediction errors. I'm going to take that elect data tibble. I'm going to pipe it to the summarize verb, which will compute a summary over my data. I'm going to make a single column in that output data, model.1.mse. It's going to be the average of those prediction errors squared, which is exactly what MSE is. Let's run that and look at the output. Looking at the output, you can see the average squared prediction error. It's 79,116,251,501. That's a really big number. OLS and many other modeling tools use mean square error as their loss function. In many cases, that mean square error can be a really big number. And this is because you're taking all the prediction errors and squaring them. So if you start with big numbers, you square them, you get really big numbers. When we're looking at the value of the loss function, we're often going to look at root mean square error instead. This is just the square root of mean square error. The square root function is monotone, which means that it preserves the order and relative comparisons. If you take a big number and a small number and take the square root of them, the small number will still be smaller than the big number, so it makes no difference in relative comparisons. The root mean square error, though, has the same scale as the errors in your data. Instead of being squared errors, you can think of it as the square root of squared errors, so it should be similar to the average of the absolute value of the errors in your data. This makes the number a lot more manageable. Looking at my code here, I have an example of how to compute the root mean square error using those model prediction errors. I'll take the electricity data, which contains the model prediction errors in model.1.errors. I'll pipe it to the summarize verb. The summary that I'm going to compute is the square root of the average of the squared prediction errors. This is exactly what root mean square error is. Let's run that code and look at the output. You can see from this, the square root of the average squared prediction error, root mean square error, from this model is 281,276. That's a much more manageable number than something in the billions. On top of that, it's easier to interpret. The root mean square error is similar to the scale of your prediction errors. So you could think, on average, the absolute value of your prediction errors is somewhere around that 280,000 number. Going through all those steps to compute the value of the loss function, adding the prediction errors to a tibble, then piping to a summarize verb, and summarizing to compute, for example, mean square error, is a lot of steps. The Model R library, though, has several built-in loss functions that make it very easy to compute the value of the loss function from a model and some data. The way these work, they're each a function. They're going to have a name based on the type of loss function. That function is going to take two arguments. First, a model that you have saved after training, and then the data that you would like to use to compute the value of the loss function. There are several loss functions built into the Model R library. Some common ones are RMSE for root mean square error, MSE for mean square error, and MAE for median absolute error. It's important to remember that the data you provide is the data used for model evaluation. It can be different from the data that you use to train the model. The only requirement is it contains all of the same features and the label that were used in your model. I have an example of using the root mean square error function here. Remember, these loss functions are just functions. I'm going to compute root mean square error, or RMSE. I'm going to use that model we trained previously, model.1, and I'm going to compute the prediction error on my electricity data in the electable. Let's run that and look at the output. And you can see the root mean square error from that model is 281,276.1, which aside from the extra decimal place is exactly what we got when we computed it the longer way before. This makes it very easy to compute the value of your loss function. Let's go back to my code. Suppose I'd like to train a new model that includes a second-degree polynomial of the high temperature. Again, we'll use that same electricity data and compute the root mean square error. Looking at my output, you can see the value of the loss function is 219,145.5. This is smaller than the value of the loss function from the previous model, so the prediction errors on the electricity data are smaller from the second model than they were from the first model. Let's go back to my code. I can do this for additional models. So first I'm going to do it for a model with a 5th degree polynomial, and then I'll do the same thing for a model with a 7th degree polynomial, and we'll look at the value of the loss function for each of these. You can see in the output window, when I use a 5th degree polynomial, the value of the loss function decreased further to 217,814.7. And then moving to a 7th degree polynomial, it shrinks even more to 217,767.6. These Model R loss functions are an easy way to compute the loss function given a model and some data.